Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll. One of the downsides, there aren't that many, but one of the downsides of being a cosmologist is that sometimes when your fellow cosmologists try to explain the important ideas of your field to the rest of the world, they cut corners now and then, or they take shortcuts, use different jargon words in specific ways, and not everything always becomes clear. A classic example of this is the phrase, the Big Bang. As I've said various times on Ask Me Anything and elsewhere in the podcast, the Big Bang phrase means different things to different people. To some people, it means the event, the moment in time when the universe was singular at the beginning, t equals zero, time equals zero, as predicted by classical general relativity. To other people, since classical general relativity is not correct, and that Big Bang singularity is just a breakdown of our understanding, they use the phrase Big Bang to mean the hot, dense, rapidly expanding, super early phase that the universe was in. People who believe in inflationary cosmology will sometimes use the phrase Big Bang to mean whatever happened before inflation. Other people who believe in inflationary cosmology will use the phrase Big Bang to mean what happened right after inflation when the universe reheats into matter and energy. Many people will use the Big Bang to be the whole model of the universe, the whole last 14 billion years, plus whatever happens in the future. That's the Big Bang model, okay? All of these are perfectly valid concepts, but they really do deserve different names. One of the simplifications that really gets in the way is the idea that because in classical general relativity the Big Bang is a singularity and therefore a boundary to space-time, that there can't be anything before the Big Bang. But as we said, the Big Bang story in general relativity can't be complete because general relativity itself is not complete. It does not include quantum mechanics. So the only honest answer to what happened at or before the Big Bang is we don't know. But of course, we're not going to stop talking after we say we don't know. We're going to say, well, maybe it was this, maybe it was that. In fact, there are many different interesting and viable models for what might have happened at or before the Big Bang. Maybe the universe came from nothing. Maybe it bounced from a pre-existing contracting phase. Maybe there's an infinite number of bounces with cycles, and we just happen to live in one of those cycles. So today, we're going to run through the options and talk about some of their pros and cons. Our guests are Niayesh Afshordi and Phil Halper. Niayesh is a well-known cosmologist in his own right at the Perimeter Institute, and Phil is a science communicator who has a wonderful series of YouTube videos. He goes by Skydive Phil on YouTube, and Phil's been interviewing cosmologists and physicists of all sorts for quite a while now, and the two of them got together to say, we got to put this in the form of a book. So the book is The Battle of the Big Bang, The New Tales of Our Cosmic Origins. And I hope that you're not disappointed to hear that they don't tell you what the right answer is at the end of the book, because we don't know what the right answer is. And that's okay. It's not because we're not smart enough or we're not thinking hard enough. Sometimes the evidence from the universe just isn't there. And what you need to do is more work. You need to develop these theories. You need to figure out exactly what they predict, exactly how they fit in with other things we know about physics. So that is what is going on. And I hope that in the process of listening to all of our talk of various different models, you don't get frustrated by saying, but I just want to know what the right thing is. I hope that you can get a sense of the excitement and the fun that professional physicists have by thinking through all of these things. And sometimes the fortunes of an individual theory will wax or wane. We think eventually we're going to get it right, but we have to go through this process to get there. And conversations like this are part of that process. So occasional reminder, you are welcome to come and be a Patreon supporter of the Mindscape podcast. You go to patreon.com/Sean M. Carroll and throw in a few bucks to support your favorite podcast. It's really not that hard to do. It's actually pretty easy. It's easier than you think if you've never done it. And it gives you a warm and fuzzy feeling. Maybe, who knows, you make the universe get understood a little bit faster by helping to spread the word that Mindscape tries to do. And with that, let's go. Niayesh Afshordi and Phil Halper, welcome to the Mindscape podcast.
Thanks for having us on, Sean.
It's great to be here.
Let me start actually with Niayesh. When I write a book, I feel very happy because it's my chance to tell the world all of my thoughts. And here, you've written a book. You and Phil have collaborated on a book, and you'll tell us the title of it. But remarkably, you do a really thorough job of talking to other people and getting their thoughts and trying to be fair to them. So, what gave you that idea of doing this kind of survey book?
Yeah, so the idea basically came from Phil. Although I liked writing a book, I thought that was a good idea, but I was very theoretical. I knew I didn't have enough willpower to do it on my own. And Universe had it in it that I met Phil at some point, and he had all the willpower that I didn't have. And he had also all these interviews, all the bona fides. He's interviewed Stephen Hawking and Andrew Linde and all the famous cosmologists who many of them I met, but he's talked much more expensively with them than I ever did. And yeah, so that was the combination. So he had all these interviews, and of course I had my own anecdotes, but I think that was a great combination.
So, Phil, tell us a little bit about the background that did go into this. Like, you've been interviewing cosmologists for quite a long time now.
That's right. I've been having a YouTube series called Before the Big Bang that's been doing for more than 10 years. And the idea was that I was interested in early universe cosmology and had loads and loads of questions, which my lecturers at university didn't know how to answer. So I thought, you know what? I'll find something on YouTube and it will explain all these different wacky ideas about what caused the Big Bang or what was the nature of the Big Bang. And there was nothing. So someone said to me, if you want to see a video like that, why don't you just make it? So I did. And I started interviewing cosmologists and I ended up in Stephen Hawking's office. And it just grew and grew and grew. And I ended up interviewing, like dozens of the leading cosmologists in the world.
That is great. And so those videos, just so our listeners know, they're out there on your channel.
That's right. If you go on the Phil Halper channel, go on the playlist that says Before the Big Bang. And some of them have had more than 1 million views. So they were very, very popular.
Now, this title is provocative, Before the Big Bang. It's not the title of your book. Your book is Battle of the Big Bang. Okay, good. But the idea that there's something before the Big Bang, I bet that some people are going to say, wait a minute, there was nothing before the Big Bang. How can you write a book about that? So I don't know which one of you wants to answer first, but why don't you tell us the classical story? Like, before you worry about quantum mechanics and extra dimensions and things like that, how do we think about what the Big Bang is and what that phrase means? Niayesh.
So the classical story, and I'm good with the classical because I'm the person who does everything classically, the old-fashioned way. It's the classical story you read in the textbooks, the kind of a story I sometimes teach, because the simplest one is that cosmology tells us that the universe has started around 14 billion years ago, and if you apply the rules of general relativity, Einstein's celebrated theory of gravity, to the universe, it tells us that it started sometime around 13.8 billion years ago, and there is really no notion of time before that. That's the classical story. That's what you would usually hear, and couldn't be farther from the truth.
Well, and tell us about the idea of the singularity then.
So I interviewed Roger Penrose, and he came up with this notion of a more robust version of a singularity. It actually goes back earlier, all the way to at least Friedman and Lemaitre in the 1920s. But in those days, it was thought to be an idealization of very unrealistic assumptions. So it was a point in time where the space-time curvature, the density, the pressure all goes to infinity. So it kind of makes sense to think that's the beginning of time. That's where space-time trajectories end, if you like. And then Roger Penrose made this much more robust. But it was in relation to black holes, what was happening in the center of a black hole. And then Stephen Hawking came along and took his ideas and said, well, look, if the future of contracting matter under certain conditions is a singularity, then the past of expanding matter is also a singularity. So there was a sort of mirror image, if you like. He could take Penrose's theorem, apply it to the Big Bang, and show the Big Bang also had a singularity. And so when those theorems were proven in the 1960s, and they had various versions, classic paper was in 1970, it was then, I think, taken that, the Big Bang was a singularity, it marks the beginning of time, and asking what came before the Big Bang is a meaningless question. Like asking what's north of the North Pole would be a very familiar phrase that you would hear. And then what happened for me was I started to become aware that people weren't taking this view particularly seriously. And I think there's lots of assumptions that are in these Penrose-Hawking theorems. And I think the one that most people will focus on is that it uses Einstein's classical theory of general relativity. But when we get to these incredibly high energy densities and temperatures, I think most cosmologists would say we need to replace Einstein's theory with a quantum theory of gravity. And what's happened in the last sort of 2 decades or so is that people have developed these quantum theories of gravity and actually started to apply them to the Big Bang. And these are speculative ideas, and we go over in the book, the various pros and cons of them. But what seems to be a common theme is that the Big Bang is not necessarily the beginning, and the singularity can be resolved.
And we're definitely going to get into that. Maybe the last thing to just clear up by way of setting the stage, Niayesh, could you tell us the difference between the Big Bang as a point in time and the Big Bang as a model for the whole history of the universe?
That's an excellent question. This is something that this thing I've always been uncomfortable with, because we meant Big Bang when scientists and we all go to conferences and we talk about Big Bang, and everybody means something slightly different by Big Bang. But Phil was the one who kind of came to me and said, we really need to sort this out. This is a problem. We have to solve it. In fact, at some point he wanted to submit a resolution to International Astronomical Union for this. So I don't think we quite got it around to that, but we did actually run a survey in a conference in Copenhagen last year, asking around 80-something cosmology, 80-something physicists working on various aspects of physics and astrophysics, what does Big Bang mean? And there were other questions we asked them, but there was only one question out of a dozen or so questions we asked them that there was a consensus that, and the consensus on this particular question was a question of the Big Bang, that the Big Bang is that early universe started from a state of hot and dense matter. And basically less than 10% of people thought that Big Bang was the beginning of time. So if you talk to scientists, they say different things and they mean different things when they mean Big Bang. So some say Big Bang, by Big Bang, they mean Big Bang singularity. Others just mean this hot beginning of the universe. But it seems that most people, and I think Phil and I agree, most people think that really what we should mean by Big Bang, this hot, dense phase of the beginning of the universe. And Big Bang singularity is really an abstraction, which we shouldn't really confuse with the Big Bang.
And also there's another confusion. I just want to be clear so everyone knows. Sometimes you'll read newspaper articles saying that the James Webb Space Telescope has seen a galaxy very early in the universe's history. This is a challenge to the Big Bang. That's neither the singularity nor the hot, dense initial state. Yeah,
so that one is just the clickbait. So this is, I think, we need to write another book on all the popular clickbaits that are used in cosmology and I guess sociology. Yeah.
All right. Well, now that you've written one book, how hard would it be to write another one? So you take a tack in the book that is, I think, exactly what a working scientist would do by examining this big question, what happened at or before the Big Bang, by looking at a bunch of models, right? Like, I mean, I don't know, did you count how many different models or theories that you have in the book, Phil?
I have, 25 different
25
models.
different models.
We don't give them all equal time, but 25 models. I think you had 17 when you debated William Lane Craig. I thought we can go more than that.
Yeah, specifically, I was just looking for ones that were eternal in time, right? So, some of yours are not necessarily. So you had an advantage over me for that. But there is an alternative way of thinking. I mean, maybe William Lane Craig is an example, but others also are, that rather than looking at models, we should have general principles and prove theorems. So, I mean, maybe Phil, could you tell us about the status of claims that we know on the basis of theorems, maybe the Borde-Guth-Vilenkin theorem, that there was a beginning to the universe, and all of this talk about eternity and before the Big Bang is a waste of time?
Right. So this Borde-Guth-Vilenkin theorem is very famous in these sorts of circles, quoted a lot. And the idea is that this theorem is supposed to prove that the universe had a beginning. So any discussion of what came before the universe is mute. But in reality, I actually interviewed Guth and Vilenkin, and I asked them this direct question: what does this theorem actually say? And at first was Guth, and he said, no, it only proves that inflation had a beginning, because there's this way of thinking about inflation, which is that it's eternal into the future. Once inflation starts, it can never stop. And so it produces a multiverse. So the natural question to ask is, well, if it's eternal into the future, could it be eternal into the past?
I'm sorry, Phil, you're going to have to tell us what inflation is.
Okay. So inflation is this period of a rapid expansion that many cosmologists believe can solve many puzzles of the Big Bang. So this rapid period of expansion is what is often thought to lead to a multiverse. We can go over why later, but the bottom line is that it's eternal into the future. Once this period of inflation, it stops in our local region of space, but not globally. So we live in one bubble of space where inflation has ended, but there will be other regions of space where inflation is still going on, and they will be making more and more and more bubbles. So Guth calls them pocket universes. But the point is, okay, so if they're eternal into the future, could they be eternal into the past? And this theorem is supposed to show that it couldn't be eternal into the past. So Vilenkin, in a popular book, did say this proves that the universe had a beginning. And lots of people have run with that quote and said, okay, any talk of a pre-Big Bang universe, or at least, an eternal universe backwards in time, that's out of the window. So when I asked Guth about it, though, he said, no, it only proves that inflation had a beginning. It doesn't prove that the universe had a beginning. There are ways of getting around it. So, for example, perhaps the universe was contracting before it was expanding. That could be a way around this theorem. Now, when I asked Vilenkin, I thought he was going to just say, yes, no, it does prove the universe had a beginning, because that's what he said in his book. But actually, he sort of backslid a bit and said, no, it only proves that inflation had a beginning. Now, he's skeptical that you could have a contracting universe, and he's got his own theory of what came before inflation, which would imply the universe had a beginning. But of course, that's a speculative idea, and we don't know whether it's right. So it's premature to use this theorem as proving that the universe had a beginning.
Yeah, no, I think let me try to summarize it, and you can see if you agree with my way of putting it. The theorem does not prove that the universe had a beginning. How could it if we don't know the complete theory of quantum gravity yet? How can you prove a theorem in a theory we don't understand? Alex Vilenkin personally thinks that the universe probably did have a beginning, and therefore maybe he was a little casual in his book, more casual than he should have been. But that's fine as long as you're not trying to prove the existence of God using that quote.
Right. Which many people have.
I noticed that if you Google the Borde-Guth-Vilenkin theorem, almost all the discussion is about religion. It's not about science, actually. But anyway, Niayesh, maybe this one is for you. This inflation idea, we're not going to get too deeply into it, but it's going to be a recurring theme in all the different models we talk about. How does that connect up with the observable universe? Inflation is something that is in this weird position, I think. It makes some predictions, but it's kind of fuzzy whether or not you can wriggle out of those predictions.
Yeah, so this is an interesting premise to talk about, because I have somewhat maybe radical fringe ideas about inflation. Maybe fringe is not the right word, but it's a bit more radical. But I guess you know scientists are opinionated, and I have
I
my own
do.
opinions. Phil, on the other hand, is much more diplomatic, and of course, he has to get along with all the cosmologists. So maybe if it wasn't for him, this book would be a little bit more stronger in its opinions, and I can probably see some of these if you read through the book. But if I want to again take the kind of party line on inflation, the main question in cosmology is how does our universe become so uniform? And inflation gives a story for that. It's basically saying that the universe was it was a tiny speck. It was very, very small. And so everything was in causal, but light could cross it very quickly. And then there is this period that can happen if you have negative pressure or vacuum energy or something close to energy of vacuum. During that period, universe can stretch by quite a bit, by 30 orders of magnitude or more in size, and then becomes big. And then that's all you need. Then the details of it, you need to put in some quantum mechanics, and you need to make some assumptions about the type of quantum things that exist in the universe. But that is a class of these things that you put can give you a lot of the things that we actually see. So in particular, cosmology is now very mature as an observational science. We have observed cosmic microwave background with very precise measurements of fluctuations in it. Basically, temperatures of this microwave background, which around 3 Kelvin, actually fluctuates by microkelvin or several microkelvin in different directions. And the patterns of these fluctuations can be predicted from these models of inflation. At least some of these models of inflation can predict these patterns with exquisite success. And that's why people are very much impressed. A lot of cosmologists are very much impressed by inflationary predictions. But then there is a catch. The catch is that there are many models of inflation, and many of them have been utterly ruled out by data. We don't talk about them anymore, but I remember, and I'm sure you remember, Sean, when we used to talk about other very national models of inflation, and we are not talking about them anymore because they've been ruled out by data. So the question is inflation really a successful theory of early universe that has been proven by data? Or rather, it's a very flexible framework that can fit anything. And the models we're talking about now just happen to be the successful ones that fit the data. But if any observation can be explained by some model of inflation, really, can you test inflation as a scientific theory?
Well, actually, that leads to a very similar question about the whole idea of talking about what happened before the Big Bang. Maybe, Phil, it's your turn. Is this doing science when we talk about what happened before the Big Bang? Like, we're not claiming to see it. How would we know if someone's model, like you have 20-some models there, how would we ever know whether one was right?
Well, I think it is science, but we have to be careful. The definition of science is quite tricky. There's not an agreed demarcation line between science and non-science. A lot of scientists will say what makes something scientific is it gives falsifiable predictions. But when you talk to philosophers of science, they're a little bit more cautious and say, actually, that's not necessarily the way we demarcate science. Rather, they're inspired by the philosopher Ludwig Wittgenstein, who had this notion of what's called a family resemblance. And basically, he was trying to define what a game was. You might think a game is something you do for fun, but, so is eating ice cream. A game has rules, but so does driving. There's all kinds of different criteria. And the idea was, well, you don't just demarcate between science and non-science by one criteria. You look at multiple criteria. But nevertheless, I think in the end of the day, it is possible to distinguish between different models of the Big Bang. And we do come up with some ideas about how we might do this. And it's not going to be easy. And we don't think it's been done yet. This is a key point, I think, that differentiates our book from many others, where they'll claim, I've come up with a model and it's already been proven. And we're trying to say, no. This field is much more uncertain. But in that uncertainty is excitement. Because the fact that we don't know means, well, there's all kinds of interesting ideas that we can explore. But ultimately, there is a potential signal that could differentiate them. And that, I think, I mean, there's more than one, but I think the one that we're most excited about is this idea of primordial gravitational waves. So these are ripples. Gravitational waves are ripples in the fabric of space-time. People will be familiar with the detection by LIGO that was caused by two black holes merging. And but the primordial gravitational waves are going to be much harder to find. They would be potentially emitted right from the Big Bang itself. So different models of the early universe make different predictions for some of the properties of these gravitational waves, whether we see them, what their spectrum is, these sorts of things. So I think it's possible that these models really can be tested. Some of them are works in progress, so it's not like they all have definite predictions yet, but that's part of doing science, I think. Your work, I love Feynman had this beautiful metaphor of speculation, but with a straitjacket. And I think that makes a distinction between a scientific speculation and a non-scientific speculation.
And actually, Phil, sure, yes, go ahead.
So if you don't mind if I add something. So in fact, there was a time back, I think in the 1800s, and we have this quote that some philosophers suggested that we never know why stars shine, what's happening at the cores of the stars. And because we cannot see and they're far away from us, they are very hot, so we cannot actually send people there. But it turns out that it happened, and we actually have a very good idea about why stars shine nowadays. And in some sense, this is the same methods that we're using now to observe the Big Bang. So we can look at quakes in the stars or so-called stelloseismology, astroseismology, which are the fluctuations or ripples in the stars, to learn about what's going on inside of them and match them with our models. And we are looking at the sound waves that are emitted at the Big Bang and potentially, hopefully, gravitational waves, if we ever detect them, to learn about what happened at the very beginning of our universe. So there are, of course, limitations, but humans are very ingenious, and maybe it's a matter of time for us to get there.
One of the exciting things that readers will get out of your book, if I'm recalling correctly, is the story of Cecilia Payne-Gaposchkin, who showed that indeed stars are made out of hydrogen and helium. She couldn't see into the center of them, right? But that's the first step along the right direction. And if I'm remembering correctly, she was the first person to get a Ph.D. in astronomy from Harvard. And the two of you were nice enough to do the counting that I was like 240th something person to get a Ph.D.
I think it was 243rd, yeah.
243rd. I didn't know that myself. So, I love reading books where I learn something about my own biography. That was great. Okay. Thank you very much for this eloquent intro to the Big Bang and inflation. And now we're going to start being more speculative, right? I mean, inflation already is a little bit speculative, but it's also totally mainstream astronomy these days. Astronomers, take it for granted almost that there's some kind of inflation. They fit models and they collect data. But when we talk about what might have happened before inflation or, was there a singularity, et cetera, now we're speculating. But the speculations have a long history. I mean, maybe, Phil, since you talked to Stephen Hawking, you can talk about the wave function of the universe and having a universe from nothing. And what were his views about that?
Well, he had this view that if you go back in time towards the Big Bang, we've got to replace the singularity. Even though he'd proved the singularity theorems, he did take the view that, well, we're going to introduce quantum mechanical effects, and they will probably resolve the singularity. I mean, ultimately, a lesson could be learned, I think, from his study of black holes. Black holes, according to general relativity, do not emit anything. Nothing comes out of a black hole. But when you apply quantum rules, you find that that's not true, that it emits Hawking radiation. So when you apply quantum mechanics to this incredible object that astronomers have discovered, you find the conclusions are different. So his view was that if we go back to the Big Bang, we will probably have something similar. Something different to the singularity will be formed. And his view was that time would effectively transform into space. So rather than having a universe which has 3 space dimensions and 1 time dimension, we would have a universe that has 4 space dimensions and no time dimension. So in that sense, you go back, but it doesn't go back eternally into the past, but there's no point that could be marked out as the beginning. So there's a sort of ambiguity about how to think about this. And I interviewed Hawking and Hartle, and my impression was they didn't quite agree on
That's
how
my
to
impression also, yes.
Okay, good. We're on the same page then. Because Hawking was quite adamant this was a universe from nothing. Because when you go back to this initial state, he thought of it as like going down to 0 radius. But I asked, and he's famous for that. That was in his book, The Grand Design. But when I asked Jim Hartle about it, he said, if I remember the words correctly, he said, "What do you mean by nothing? In quantum mechanics, there's always something." So I get the feeling they didn't interpret this quite in the same way. Interestingly enough, there's another colleague of Jim Hartle called Aaron Wall, and he wrote a blog post saying, well, actually, there's this thing they use called imaginary time. So imaginary time is a sort of mathematical trick, if you like. It's people who know mathematics will know there are these things called imaginary numbers, where normally you might think if you think of the square root of 9, you might think, okay, we know the square root of 9, it's 3, but it's also minus 3. Now, if I ask you what's the square root of minus 9, you're going to go, what number times itself will give you a negative number? Well, there's no conventional number that would do that. But mathematicians invented these things called imaginary numbers. So they have this thing called imaginary time, which is sort of parallel to that, if you like. And Aaron Wall suggested, well, the beginning is in imaginary time, but we can also think of the universe in real time. And there, the Hartle-Hawking model actually has like a bounce. And so now I asked another collaborator, Thomas Hertog, I said, well, does this mean the universe doesn't have a beginning in the Hartle-Hawking model? And he's like, well, the arrow of time points away from the bounce in both directions. So that's really a beginning. And so how to interpret the maths is actually something that I think the originators of the Hartle-Hawking model don't necessarily agree on. But they do agree it's a very promising idea.
Well, so this is then my question for Niayesh as the professional cosmologist. Is this idea of calculating the quantum wave function of the universe taken seriously by the working cosmologists?
Well, I guess both of us are working cosmologists, so I don't want to annoy you if I say something. But what I like to think is, certainly something, it's a goal. You want to have a wave function of the universe, and there are different ways of doing this. In fact, where I'm sitting right now, next door used to be Stephen Hawking's office when he visited Perimeter. I talked to him a little bit. I think our interactions were not quite as fruitful as Phil's, but I did talk to him a little bit about his ideas. And the other person who used to sit next door is his funnily same office. It was Neil Turok, who was the director of our institute, and they couldn't agree about whether this wave function made sense.
Right.
So Neil Turok and his collaborators believed that it didn't make any sense, or Hawking's calculation of the wave function didn't make any sense. But of course, Hartle and Hawking thought that what they did is a proposal, not necessarily unique, but is a well-defined proposal for the wave function. So definitely there is no consensus amongst professional cosmologists. And in some sense, proposing a wave function from the beginning of the universe is a proposal. There is no right or wrong for it. It's just a proposal that then you should kind of go and test. The question is it fully self-consistent in terms of its predictions? And there is an argument about that. But really, I think the answer to it is that there is one version of it, which Neil Turok was thinking about, which was not fully self-consistent, and there was another version that Hartle and Hawking were thinking about, which at least in their view is self-consistent. And there are two different versions. Obviously, if you're proposing something, it's up to you what you're proposing. So that's the story from my point of view.
I just add one thing. One thing you can do is, even as a layman, if you want to know if other scientists are taking an idea seriously, is that you can look at how many citations a paper has. That doesn't say it's right. Absolutely
Right.
doesn't say it's right. But it does say that other scientists are taking it seriously. And the Hartle-Hawking model, the original paper has thousands of citations. So that tells you that other cosmologists are at least taking the idea seriously. But it doesn't tell you that it's the actual correct model of the universe.
No, I think that's an excellent point, and thank you for saying that, because I think that I do want to empower the listeners to check these things for themselves. And you can go to Google Scholar or Inspire, which is another service, to look for these numbers of citations. And one thing I like to say, maybe somewhat tongue-in-cheek, but it's better to be first than to be right in science. If you have an idea, other people can fix it. Like if you can have flaws in the idea, inflation had flaws in the idea, but it's a new idea. It gets people thinking in new ways. And I think that the Hartle-Hawking wave function of the universe was certainly that.
Definitely.
That's right. So I guess one thing I would add is, I mean, even though it's a proposal, the thing that's missing from Hartle-Hawking proposal is generally quantum theory of gravity. And we know
Sure.
that general relativity is not a complete theory. And in some sense, to my mind, I mean, again, personally speaking here, is that it cannot be the full story because it's just based on theory of general relativity that we know is incomplete. So again, it's a good and interesting starting point, but it's missing something.
Well, that's a good point, because many of the people who you talk to in the book think they do have the right theory of quantum gravity, even though they don't agree with each other. So one of those approaches, of course, is string theory. We've talked about string theory a number of times on the podcast. What is the intersection of string theory with this question of what happened at the Big Bang?
Well, I think the simple answer is we need a quantum theory of gravity to describe the Big Bang. And people think that these theories maybe can never be tested because the energy of particle accelerators is nowhere near the quantum gravity regime. So there's no realistic prospect of ever building a particle accelerator that can probe this. However, the universe has done it for us because the Big Bang has those energies. So the idea is that maybe what we could do is develop a model of the Big Bang using principles from some quantum gravity idea, be it string theory or some alternative theory. And then maybe that will give us some new ideas and maybe novel predictions. And then maybe we could test those. And so in the book, we talk about a lot of different ideas that people have played with. Unfortunately, with string theory, there's not one idea that's come out about the Big Bang. So Robert Brandenberger, I think, was the first, and he came up with this model called string gas cosmology. And then we have Gabriele Veneziano, who people may know is the sort of father of string theory. And he's come up with his own model called pre-Big Bang. The most famous model is the ekpyrotic model. That got a lot of press attention. And that's this idea of, well, there are these higher dimensional brains, and they collide, and when they collide, that heats up the universe, and that's the Big Bang. So there's several different ideas in string theory, and of course, some string theorists will say, actually, what it does is it gives you inflation. So maybe string theory will give you new fields, and one of those fields will be the field that people have associated with inflation, which we call the inflaton. So there's a very active research program and lots of different ideas, no consensus yet. But what I think it does show that's very interesting is that maybe we can test these theories of quantum gravity by applying them to the Big Bang and then looking for observational signatures.
Well, we did have Kumran Vafa on the podcast, but we didn't talk about string gas cosmology, which I think he and Robert Brandenberger pioneered early together. I remember coming across it when I was a young, impressionable graduate student and thinking it was awesome. These days, I don't think it's that awesome, but let's tell the audience what it is. Maybe Niayesh take a stab at it, and you can tell us whether you think it's awesome, and then I'll give my take.
Absolutely. So yeah, I know both Robert Brandenberger and Kamran Vafa very well. Kamran Vafa is also another Iranian scientist now at Harvard, and has been at Harvard for a long time. Robert, we also go way back because I first started working with Robert as a graduate student back 20 something years ago. Um, and of course, yeah, this was his favorite theory of the Big Bang. It wasn't an inflation theory. And the idea was, if you think a string theory, and I guess the string theory, yeah, most people have heard about it. The idea is that the fundamental degrees of freedom are not particles, but these tiny strings, and everything you see in the universe is somehow interaction of these strings that leads to particles, and gravity and the entire universe are come out of properties, emergent properties of these strings that are interacting in a quantum way with each other. So Kamran Laffa and Robert Banneberger, they were both at Harvard at the time, back in the 80s. And they kind of got together, and that was when a string theory was like a young theory, young proposal. Not many people have thought about it. And I started exploring what it would imply for the early universe, which, as Phil mentioned, is the place where you want quantum gravity to understand what's happening. So they thought of a hot universe, but instead of particles, you had the strings in it. And the one thing that they knew from a string theory is that a string theory has extra dimensions. Somehow a consistent theory of quantum gravity with the strings doesn't work in 4 dimensions or 3+1 dimensions that we see, 3 space and 1 time dimensions. You need to add more dimensions to cancel some so-called quantum anomalies, which are some problems, some infinities that you want to get rid of in a proper quantum theory. So you need extra 6 dimensions that we don't see. And to this day, one of the problems with the string theory is what happened to these 6 dimensions? Can we somehow get rid of them? What do we do with them? Are they there? Are they not there? And one of the first ideas was, at least in the cosmological setting, the idea that somehow, if you had a hot gas of the strings in the early universe, their interaction could lead to 3 of these dimensions getting big, as we see them, and then 6 of them are staying small. So that is one of the things that a string gas cosmology, that is the original version, could address. And there could be other things that still I don't remember very well. But so it's a very cool idea. So if you imagine like two strings or 2 lines in 3 dimensions, if you imagine 2 lines and then one of them is moving, almost always they intersect with each other, right? So it's just kind of randomly moving each other. So 2 lines, they move in random direction with probability of 1, they intersect with each other. In higher dimensions, the probability is 0. And this is amazing. So the string theory, you have these 10 dimensions in which the strings are moving. But so that means that if they're just moving randomly, they're almost never intersect with each other. But if somehow 2 of the 6 of these dimensions were much smaller, then the probability of intersection would be much higher if you could kind of shrink or compactify these 6 dimensions. So the details of how they work with this is more technical. But at the end of the day, they use this geometric fact that 2 strings almost always collide with each other in 3 dimensions, and in higher dimensions they don't collide with each other. They use this fact and basically some of the physics of string theory to show that it's possible that the early universe, 6 dimensions of a string theory become smaller, stay small, but 3 of them could expand. And this was kind of the beginning or the key idea of string gas cosmology. Now, Robert has kept working on this with collaboration with Wafa and other Robert Banneberger in collaboration with Wafa and others. They have more recent results on predictions for gravitational waves that may come out of a string gas cosmology that's different from gravitational waves that come out of inflation. But that was where the key idea come from.
So hang on, Sean. I want to add one extra thing. One thing that I think is particularly exciting about string gas cosmology is that if you compress a box of particles, it will heat up and heat up and heat up. And indefinitely, you get this infinite temperature at the singularity. And the claim, at least in string gas cosmology, is that can't happen, that there is a maximum temperature And then if you try and compress it after that, it will just go back down. So again, we got this hint that maybe the Big Bang wasn't the beginning. And that's a very interesting feature of string gas cosmology.
It was an early invocation of duality in string theory.
Yes.
But okay.
That's right. So, yep. Go ahead. Yeah.
So I just want to understand the large scale story that string gas cosmology is trying to sell us. We have 9 dimensions of space. They're all very small. And then in 3 dimensions, they start unwinding and getting bigger. Is that the basic picture?
Mm-hmm. That's right.
So,
and the 6 stays small.
But did the 9 dimensions, were they small and more or less sitting there infinitely far into the past?
Yeah, so that's part of the story, which is not entirely clear. But I think, as Phil was mentioning, there is this a story of duality in a string theory, where when things become very, very small, they are identical to them becoming very, very large. So there is a scale of basically T-duality in a string theory, where when you said the very big things, the story of very big things is the same as the story of very small things if you kind of flip the scale with the right rules. And that's what they're using. So the idea would be that if you go to early times, things get very small. Now, I don't think there is an entirely coherent story. I think originally maybe there was the idea of a bounce, that maybe universe was getting small, and then when it reaches this high temperature, so-called Hagedorn temperature, then it would bounce back. The more recent version that I've heard from Robert in the past, I guess 10, 15, well, maybe 20 years, I think early 2000s, the idea is that maybe universe is sitting in some uniform temperature phase and nothing is changing. It's like an equilibrium. And then it spontaneously kind of slowly moves away from equilibrium and starts expanding. And to be honest, I don't really know if there is, which one of these sound more plausible.
I know which one sounds more plausible. Sorry, that second one does not sound plausible at all. As you know, I have deep care about the issue of the arrow of time and the beginning of if the universe could stretch back to minus infinity. So I'm very skeptical of the story that says the universe sits there doing nothing for infinity years, and then part of it starts expanding. That doesn't seem quite right to me.
So this is called the Emergent scenario, and people have played with this. Famously, George Ellis came up with a model like this, and then Anthony Aguirre and Cahias criticized it, saying it couldn't sit there. Vilenkin and Matani have criticized this, and I think basically on your page, Sean, saying it couldn't just sit there forever. So although Anthony Aguirre is a fan of a past eternal universe, he doesn't like that model. But other people, have played with these ideas. And some people say, well, you could introduce fields that would stabilize it. So I think it's still an open question, but I would bet if you polled cosmologists that they would probably say the emergent universe is not the way to go for an eternal past eternal universe.
But the possibility that the scenario does bring up another very popular angle in pre-Big Bang investigations, which is the possibility of a bounce. Like maybe you could use this string gas cosmology story to say that there's a reflection around some moment in time that we think of as the Big Bang, and it's expanding and cooling in both directions of time after that. But tell us about the sordid and confusing history of bouncing cosmologies, because this is an idea that has been pursued a lot, but also in a lot of different ways. Maybe, Phil, you can go first.
Yeah, well, the first people came up with it, all the way back to the Big Bang, actually, because Gamow is known as one of the main proponents of the Big Bang theory, but he actually didn't think it was the beginning of time. He thought there was a contracting universe and then an expansion. In fact, he called the model the Big Squeeze. Interestingly, Dickey was another cosmologist, very famous for almost kind of discovering the CMB. Yeah. There's a long story about that, but he was looking for it, and then he got scooped by Penzias and Wilson. Although there's an interesting little twist there, because it was actually discovered by McKellar 20 years earlier. But that's an aside. Dickey and Gamow were key figures, and they believed that the universe did bounce. Now, this idea, I think, got put to the back burner for quite a few decades after the 1960s. There was a paper by Guth and Scher that showed that you couldn't have a bouncing universe, that it was impossible. And I think that was the consensus view. Then along comes, a model like string gas cosmology and ekpyrotic models, and they seem to, at least in some versions, imply a bounce. And then the rival to string theory, loop quantum gravity, they started doing cosmology in the early 2000s, and they ran simulations using their theory. And they also seem to see a bounce. And there's a wonderful analogy that Martin Boerewald uses. He's one of the researchers in loop quantum cosmology, although he had become a critic of the mainstream version of it. But
I can tell the audience that there's a lot of skeletons in the closet and dirty linen exposed in your book. There's some rivalries there, but go on.
Oh yeah, that's one of the things we thought would be fun to do in the book, to get all the dirty linen and the skeletons out in the open. But anyway, Boerewald has this wonderful analogy where he uses this idea of a sponge. So if you pour water on a sponge, it will absorb the water, but only up to a certain point. It can't keep going indefinitely. If you pour more and more water, eventually the sponge will switch its properties from becoming water absorbent to water repellent. And the idea is that space would have exactly the same property in a way. It would get full up. And so rather than gravity becoming attractive, it would become repulsive. So if you run a simulation of the universe as you go backwards in time, you get to this repulsive point, and then the universe bounces. So you get an hourglass cosmology. Now, the hourglass, a lot of people think that this is a cyclic universe, but not necessarily. It could just be there's an expanding phase mirrored by a contracting phase. And there's all kinds of variations on this hourglass universe. They're not all the same. Some have a reversal of the hour of time at the bounce, some don't. But nevertheless, it does, in our book, we survey many different models. And this idea of a bounce does come up many, many times in many different frameworks. So although I'm not convinced there was a bounce, I do think it's at least a plausible idea that we should entertain.
Niayesh, where are you coming down on this?
Yeah, it's a tough one. I think bounce on the one hand, it's very plausible. I mean, if I throw a ball on the floor, it bounces back. But
that's very scientific.
If I throw it, yes, very scientific experiments I run. Yeah, but then if I throw almost any other things on the floor, it doesn't bounce back. So based on my experiments, yeah, the probability is not very high for the bounce, let's say. And I think maybe on a more serious note, and we were just talking about these emergent universes compared to the bouncing universes. The problem with the bounce to me is that you kind of push back the problem of the beginning of universe to some earlier period, and you still somebody has to tell you what happened before.
Right.
Now, if you reverse the arrow of time, that's kind of interesting because they say, okay, so there was no before. So there was some point in which time reverses, and then we have to set up the rules there. And that could be reasonable because then I can set up the rules there and I'm done. But if I have to just keep pushing things back, then I don't really have a coherent kind of a story because I'm just pushing things back to an earlier time.
Yeah, I don't want to keep interjecting my own views here, but it is my podcast after all, and I have thought about these things. So my thing about the bounces is, and you've already laid it out basically, but there's basically two choices. There's sort of a smooth evolution of entropy in the arrow of time in one direction through the bounce. And if that's true, then you need an infinite amount of fine-tuning in the far past to make it work. Like entropy has been increasing for infinity years, and that's just weird. But the other alternative, which I think the first paper that I know about was from former Mindscape guest Anthony Aguirre and Stephen Grattan, where you have a bounce where the arrow of time is pointing in opposite directions on both sides of the bounce. But there, you need an infinite amount of fine-tuning at the bounce, right, to make it exactly work out. So I'm kind of a bounce skeptic myself.
Well, I think the people that propose the bounce, they sort of have their own idiosyncratic views on entropy, and maybe that they propose different ideas. Like Carlo Rovelli, for example, thinks that entropy is some kind of observer-dependent effect. So it's not that the universe is really low entropy at the Big Bang. It just seemed that way to us. Others have suggested there's some sort of reset mechanism. So there's all kinds of different ideas about the entropy. And of course, you've come up with some brilliant ideas yourself that we cover in the book. But we should add that there's no consensus about how to treat the entropy. But it is an absolutely fascinating puzzle.
Well, and you mentioned you gave a certain amount of time to the idea of a bounce in loop quantum gravity, but we've already mentioned string theory, and you mentioned the word ekpyrosis or the ekpyrotic universe. So maybe explain a little bit about that. It's a stringy bounce that is a different idea than string gas cosmology. I don't know if Niayesh, you want to take it.
Sure. So yeah, I remember when I was a student at Princeton, and that was, I mean, of course, inflation was the big thing there, and then WMAP was the CMB experiments coming out. But suddenly, out of nowhere, came this paper. I think it was called ekpyrotic cosmology, and it was possibly the first serious contender against inflation, so that raised a lot of eyebrows. But I remember, I think it was Paul Steinhardt, Justin Curry, Bertov Ruth, and maybe one other person. I can't remember.
Neil Torok.
Oh, of course, Neil Torok.
Yeah.
Yes, that's why I couldn't remember. Yeah, so that was. I mean, so that all the people that there at Princeton. In fact, I remember at IAS, I think Paul Steinhardt gave his talk about how you could have basically two brains. So brains were all the rage back then. So the idea was that somehow there are these extra dimensions that we talked about, but we don't see them because we're stuck to these brains. So everybody was talking about brain wars back then. And then they took this idea. Bert Avroth was a string theorist, Paul Steinhardt cosmologist, as was Neil Turok, and Justin was a student at the time. So they said, okay, let's take these brains and then think about them in the Big Bang. What if Big Bang was when two of these brains collide with each other? So that's where it all started. And then try to kind of set up a calculation for cosmology with the extra dimensions and these brains. And they came up with this scenario where you could basically, you have a contracting universe. And it seems like that from our point of view, there is some sort of a singularity, but from the higher dimensional point of view, it's all okay. And they had a way of kind of going from a contracting universe and something that looks like a singularity to an expanding universe, and making a lot of entropy at that point. That was the first paper. And then from there on, they kind of tried to work at perturbations. And there was a lot of controversy about, can you get the same spectrum of perturbations as inflation? They thought that there's a very similar process with quantum fluctuations in ekpyrotic cosmology, similar to what happens in inflation. There were others who said, no, this doesn't work the same way. So they had to invent extra stuff. And yeah, so that was where ekpyrotic cosmology started. I think a lot of people have grown colder on it. Even I think the people who started it, I don't think they talk about it as much. I think Neil Torok likes a singularity of some sort. Paul doesn't like singularity anymore now. He wants a smooth bounce now. I think there was a lot of interest and excitement early on, but right now I think people haven't been working on it as intensely as they used to.
Oh, I just want to add something, that the picture of the colliding brains has been dropped by the people still pushing the ekpyrotic model. So you can still, what they do is basically saying, well, let's take the good bits, the idea of some kind of cyclic universe, and we can model like a scalar field that will propel that. And let's keep that. Let's drop all the discussion of the colliding brains. We don't actually need that.
Yeah.
So Paul Steinhardt has worked with Anna Ias, and they are still working on this model. And recently, they've claimed, they've worked with the numerical relativists, and they've claimed that they can get, a smooth universe, and they can smooth the universe just as well as inflation can. So, of course, that's a controversial claim, but this is part of the excitement of doing early universe cosmology. What would really happen in these scenarios.
And just so people keep the players straight on the scorecard, Paul Steinhardt was a pioneer of inflation and new inflation in particular, and developed a lot of the tools of the perturbations and so forth. But he later became very concerned that inflation, if it's eternal, it doesn't predict anything, and therefore he's been looking for alternatives. And I think we all agree, you'll correct me if I'm wrong, it would be great to have as many compelling alternatives to inflation as possible. There just aren't that many right now.
That's right. I mean, I think the way science works is like a competitive process. If you want to overthrow inflation, you better come up with something better.
Yeah.
So that's the game. Come up with something better, and that's what they've tried to do. Paul is very critical of inflation, as many people will know. He was one of its leading defenders. What happened was, when Alan Guth first proposed inflation, there was this issue called the graceful exit problem. And that is, they couldn't get inflation to end. Paul and his student, Andy Albrecht, they came up with a solution. Roughly the same time, Andre Linde came up with basically the same solution. And so Paul was a great defender of inflation, but over the years, he soured on it. And I think it was the multiverse. I mean, I interviewed him, so I know exactly what it was that turned him against it. And it was the multiverse, this idea that if you have inflation, then it will be eternal, and this will generate a multiverse. And if you have a multiverse, then you can't make predictions. Anything can happen. So inflation's not predictive. Therefore, we need to come up with an alternative. So they tried this colliding brane idea. And I think when supersymmetry, which is a property of particles that was hoped to have been found at the LHC when it was running, it switched on in like 2010, something like that. People were hoping to find this property called supersymmetry, which is something string theorists, had put some faith in, shall we say. It wasn't found. I don't think that disproves string theory, but it certainly, was a little bit of a knock. And so they wanted to detach the ekpyrotic model from its string theory roots. And so that's why they've sort of said, okay, we can still have an ekpyrotic contraction phase. We just don't need to worry about the colliding branes anymore.
Okay, but ironically, even though part of the motivation for the ekpyrotic bouncing universe was to get away from the problems posed by an inflationary multiverse, some subset of the people who invented it went on to champion a cyclic cosmology, where you sort of have bounces and many phases of bouncing, and then you get a multiverse in time instead of in space. So, all right, who wants to tell me? Maybe Niayesh, it's your turn to talk. Tell me about the cyclic version of either that or somebody else's favorite cosmology.
Yeah, so this idea of cyclic cosmology is also very old. I think Phil would know the history maybe better than I do. In fact, I think there was even in a movie. Wasn't there a movie that Gold, Bondi, and Hoyle watched?
It was called The Dead of Night. It was a horror film, and the idea was that it was like a ghost story, and if you watch the film and you kept going, it would come back to where it started, and that inspired Bondi, Hoyle, and Gold.
I never heard the story.
Yeah. Oh yeah, they were like, okay, you can have a story which actually has evolution, but it doesn't have a beginning. Any point is as good as any other point. You can start the movie anywhere you like, and if you watch it on a loop, you keep going. So that movie inspired them. But of course, the idea of a cyclic universe goes back thousands and thousands of years. Yeah. The Stoics, they were Greek philosophers, but of course the Hindus, the Buddhists, they all liked a cyclic universe. But go on, Niayesh.
So the nice thing about the cyclic universe, and I think kind of goes back to my answer to the bouncing story, is that, okay, so what happened before the bounce? And if you just have to keep pushing this back, then we don't really have a fuller story. And one nice thing about the cyclic cosmology is that maybe that you do have a fuller story, just everything happens in the loop. And it also kind of matches a lot of things we see in everyday life, that we see things keep repeating. Of course, not exactly, but the cyclic cosmology things maybe more or less exactly keep repeating themselves. Now, these cycles have different forms. in some sense, if the universe was closed, in the early models of cosmology gave a natural possibility for cycles, because if your universe expands and then it stops expanding and then contracts into a big crunch and then big bangs again, so maybe that's the way of doing cycles. That doesn't quite work, maybe because maybe the cycles wouldn't be identical, but maybe they don't have to be identical. And there have been a lot of controversy about, okay, so can you have identical cycles? Because maybe entropy should always increase. But then on the other hand, in infinite universe, entropy is infinite. So what does it mean to say that entropy should always increase if it's infinity? So there are many versions of cyclic universe that some are my favorites. So the ekpyrotic model, for example, gives you an opportunity because they had a bounce already, at least some version of a bounce that they liked. And they kind of added a little bit of bells and whistles to it. Basically, assume that there is this dark energy that plays a particular role. So dark energy right now causes the expansion of the universe to speed up. But they imagine that this dark energy, if you wait long enough, could actually become negative and cause universe to collapse. And that leads to the basically contracting universe and bounce that was originally part of ekpyrotic cosmology. So that's that version of the cyclic cosmology. Roger Penrose has another version, which has been criticized a lot for reasons that are not very much related to the original idea, but to some kind of weird claims that Roger Penrose makes. So Roger Penrose had this very curious idea that maybe you have cycles of the universe, but the cycles last infinitely long. So if they last infinitely long, you would think, okay, how do we know that it goes in cycles? But then there are different ways of defining time. According to one observer, it lasts infinitely long, but according to a different type of observer, so-called conformal observer, maybe it actually lasts a finite time. And then the end of the universe, this heat death of the universe somehow could be matched to the Big Bang. Even though one is infinitely cold, the other is infinitely hot, but nonetheless, somehow they could be matched if in this conformal weird way of thinking about time, which is Roger Penrose's favorite way of doing things.
You have to be Roger Penrose to think of these things, right? No one else could have thought of these ideas.
I think others could have thought about these ideas, but nobody would have taken them very seriously. Right. So, for example, with my students at school, we thought about kind of a way of explaining the spectrum of cosmic microwave background in this context of Roger's conformal cyclic cosmology, where the future evolution of universe and the past evolution in a consistent way would match each other at this matching of the Big Bang to heat death. And that actually puts some constraints on the kind of perturbations you could have in the universe. Then there are other models of cyclic cosmology. Maybe you have a phantom dark energy. So the universe, its dark energy we see right now, could have, if it has enough negative pressure, universe could actually blow up in a finite time. And then that could be the next Big Bang. So that's another possible idea. And there are many more in the book that we go through.
It does seem to me, I don't know, Phil, maybe you give, because you've talked to so many people about these things, it seems that there is a naturalness to the idea of either a bounce or cycles, but when you actually try to make it work, you kind of lose some of the simple robustness of the inflationary model. You add all these extra fields and you have to like play around to make, and maybe the universe does that, but inflation just is so simple to state what you need, and these others seem like Rube Goldberg machines to me.
I think it depends on the individual model. So some of them are quite simple, I think, like the loop quantum cosmology one, that gives you a bounce, and you don't need to introduce any extra fields at all, as far as I'm aware. You just have the theory of quantum gravity that they've developed, corrections to the Einstein's equations, you follow it back in time and you get a bounce. Now, that's not a cyclic model. So
I guess, maybe I should be more fair to the bounce models. Okay.
Yeah. So now for the cycles, I mean, look, the ekpyrotic one has extra fields, so they can't. But then you could say inflation also has to assume a hypothetical field. So what's the difference? Now, inflation, of course, only needs general relativity and quantum mechanics. It does, I think there's a lot going for inflation. It seems very intuitive. It's why can't the universe expand exponentially? Sure, it can. It is a very attractive idea, but there are things going for some of these other models. I mean, I think people have complained that inflation doesn't solve the entropy problem. And what's the motivation for some of what's surprising? A lot of people think, oh, you can't have a cyclic cosmology because of entropy. And there's a reasonable argument to have there. But the motivation for Penrose developing his cyclic cosmology was to try and tackle the entropy problem. Now, of course, he has a very novel solution. He's got to assume certain things, like he has to assume that mass will disappear in the very far future. That's not something I think a lot of physicists would be particularly comfortable with. But what Penrose says, he has this great quote. He called inflation a fantasy, but it wasn't a pejorative term. What he was saying was something fantastical had to happen at the Big Bang. And maybe it was inflation, but maybe it was something else. So when Roger comes up with these fantastical ideas, we might look at them and go, are you crazy? And in fact, he calls it a crazy idea. But something crazy had to happen. So I'm less keen to write off the cyclic models as having too many bells and whistles. They definitely have problems. And when in the book, we go over what the problems are. But I think every model has some problem. And the task of the cosmologist is either to say that's a fatal problem, let's move on from that, or maybe we can fix that problem and we can get a really interesting model of cosmology.
Maybe for Niayesh, what are the prospects for actually getting data that will help us about this? Obviously, we're looking for clues in the cosmic microwave background, maybe gravitational waves, maybe something else. I don't know. What other things could we look for in addition to that? And what are the prospects for actually finding gravitational wave signatures?
Well, one may argue we found the gravitational wave signatures from the Big Bang. It was 10 years ago. We just lost it. It was there. There was a good few months where we had discovered gravitational waves from the Big Bang, and there were all the headlines were buzz for that. But then, as my good friend Brian Keating, I guess, wrote the book about losing the Nobel Prize. They almost had the Nobel Prize in their hands when they discovered these gravitational waves. It turns out it wasn't gravitational waves after all. It was polarized emission from dust in our galaxy.
Right.
And we have to be aware of that. And I think for every big discovery, there's always this chance of a false alarm that may come around. But but really, there are opportunities out there, and we have made big discoveries in cosmology. We learned about dark energy. We learned about cosmic microwave background. What's going to be the next big discovery that will tell us, at least get us closer to understanding what happened at the Big Bang? And I think, as Phil mentioned, gravitational waves is one of the most ambitious ones. We've already discovered gravitational waves from merging black holes and neutron stars. That was an amazing feat, which deservedly won the Nobel Prize and many other prizes by the LIGO and Virgo collaborations. If we push the technology on that front, the next step is going to be LISA observatory in space, which is basically gravitational wave detectors, but then satellites out in the solar system. That might have a chance of at least getting us the right technology and the right direction to detect much longer wavelength, much smaller amplitude gravitational waves. And eventually, I mean, some of the proposals out there, there's this Big Bang Observatory that we talk a lot about just because it's so ambitious, could get us actually close in the ballpark of the amplitudes of gravitational waves we may expect from the Big Bang, or from, say, some models of the Big Bang, like some inflation models.
Sorry, tell us what the Big Bang Observatory would be.
Right. So Big Bang Observatory is kind of based on the same idea as LISA, but it's much kind of higher technology, much better technology. And basically, the idea is that you send these spacecrafts into space, into orbits, in the orbits in the solar system, going around the sun, basically. And they have lasers that send to each other. So basically, they're laser receivers, and it's very powerful lasers, and then very, very precise receivers of these lasers at millions of kilometers distance from each other. And the same technology that LIGO uses, the idea is for these satellites to use, which is basically based on the interference patterns or basically the signal of these lasers that are received from different satellites. You could measure very precisely the distance between these satellites. And this distance, if there's a gravitational wave that passes through, these distances will oscillate with time at the frequency of these gravitational waves. And LIGO has successfully used this technology on Earth to detect gravitational waves, basically tiny, tiny ripples in the space-time geometry to like 1 part in 10 to the 28 or so. So like 1 with how many? 20 zeros in front of it. So it's a tiny, tiny fluctuations. And LISA in the next decade or so is going to do this in space, hopefully. And I mean, that's according to all plans, that's going to happen. Hopefully, if there is no big, the US government and European governments don't collapse in the next 10 years. But then if that goes through, then hopefully if there is enough will and investment, then the next step could be to push this technology to a level that they could detect gravitational waves from the Big Bang. But also you could detect these gravitational waves in the cosmic microwave background if we are lucky, and we could kind of avoid the problems that 10 years ago BICEP had. We could kind of cleanly separate the signal from the dust in our galaxy from other signals, from the other signals and the clean gravitational wave signal from the Big Bang. If they can be separated successfully, then maybe we could actually see these gravitational waves in the cosmic microwave background. Another front where there could be progress is like subtle statistical properties of microwave background, or in the galaxies. In fact, another thing that we are witnessing a revolution is the number of galaxies we're observing is kind of keeps increasing like tenfold every 10 years, I think, or something like that. I haven't really seen the Moore's law for galaxies, but I'm pretty sure there's a Moore's law for the number of galaxies observed.
Can't go on forever. Cannot go on forever.
I don't know. Oh, yeah, probably not. We're going to run out of galaxies soon. I think SDSS saw 1 million galaxies. DESI, which is dark energy spectroscopic instrument, had big press releases in the past couple of months. They're going to observe 30 million galaxies with instruments like SphereX or Rubin Observatory. We're going to go maybe up to 1 trillion galaxies. And with that much data, we are hopefully we are going to detect subtle statistical signatures of the kind of things that could have generated our initial conditions. There is this thing called primordial non-Gaussianity, which is another prime target for Big Bang theories. Basically, roughly speaking, are there the same number of hot spots or cold and cold spots in the microwave background? Or in galaxy overdensities, are places that galaxies are a bit more overdense and a bit more underdense. You could, there are effects that are just purely astrophysical that could lead to this, but if we could separate them from the primordial effects, just from the Big Bang, that could distinguish many different Big Bang models or rule many of them out. And that's going to be also very exciting, something that I'm looking forward to in the next maybe 10, 15 years.
That's good. I'm glad we got to like ground ourselves in the experimental data a little bit. I know that we've covered a lot of models. There's even many more models in your book. We don't have an obligation to talk about every model, but I will at least give each of you the opportunity to tell me if there's one model that we haven't talked about that you really think we should, or is your favorite, or even just like kooky and fun. So Phil, you can go first.
Well, one thing we haven't mentioned is the idea that the universe came out of a black hole. Black holes have singularities in them. The Big Bang was a singularity, at least in general relativity. So maybe the universe came out of a black hole. Maybe they bounce and create a new region of space-time. One idea I quite like, or it's got less attention than I think it deserves, is this notion of cosmological natural selection. So this is one possible solution to what's called the fine-tuning problem. This idea that if you change a constant nature very slightly, You wouldn't get life. So how is it that we have life-emitting values? There's all kinds of different approaches to this problem. But one obvious parallel is with the genes. Like if you randomly put genes together, you're not going to get a living organism. But hey, if there's a Darwinian process at work, then you will get a working organism, no intelligent designer required. So Lee Smolin came up with an idea that maybe black holes give birth to new universes, and their daughters, as it were, would have very slightly different values for the constants. And then you'd have a selection pressure. Because the universes with more black holes would have more daughters or children. So I think this is an ingenious idea. I don't know if it's true, but there are other variations that the universe could come out of a black hole. And in fact, I think we have at least 3 in the book. So that's one we haven't mentioned. Oh, and one other thing, I've got to say one thing, is Niayesh briefly mentioned it, but I've only hinted at it. And that is the idea that maybe there are what are called closed time-like curves. And these are where the curvature of space-time gets so extreme, it actually forms a loop and you can travel backwards in time. And wouldn't that be a neat idea to explain where the universe came from? It gave birth to itself.
All right, Niayesh, you have a favorite one that we haven't mentioned yet?
Yeah, my favorite one is if things or signals can propagate faster than the speed of light, or maybe another way of putting it is that the speed of light is not really an absolute limit. If you go to extreme situations, maybe high temperatures, for example, signals can propagate arbitrarily fast. And the reason that one is my favorite, and I think maybe you worked on it, Sean, at some point. Well, I think you worked on lots of things, but I think maybe early on you worked on this faster than the speed of light, or ether theories, I guess, maybe another way that maybe ether was not really disproven. Maybe they were just subtle. There is ether out there, and signals can propagate faster than the speed of light.
Right.
And the reason I like it is that it actually can connect to a lot of different things. It's not just one model for one thing. Like inflation is one model for early universe, but it doesn't really address other problems we have in fundamental physics. But this faster than the speed of light travel, even though it has its own problems, and I mean, the biggest one is that why don't we see it? I mean, we see that relativity is very successful today. But nonetheless, at the fundamental level, it could address a lot of issues. For example, it could be a theory of quantum gravity. It's known as Hojava-Lifshitz gravity, which you could make quantum gravity renormalizable by a particular flavor of faster than the speed of light travel. If you kind of more energetic particles can propagate much faster. But it also can give you a scale invariant spectrum of perturbations in our universe, which is the kind of thing we need to explain cosmic microwave background data. It's something that many people have worked on, but in particular, Zhao Magoija and I have worked on, and it has very specific predictions for, say, tilt or non-Gaussianity of perturbations that come out of the Big Bang. And it also could tell us something maybe about the measurement problem, because in some sense we have this issue with non-locality of quantum mechanics and how to interpret it in terms of non-local hidden variables. But if really there is no limit on a speed, then maybe we could have a realistic interpretation of quantum mechanics and don't have to worry about instantaneous signal propagation. So I don't have any concrete proposal that matches all of these together, but it seems that there might be the right ingredients in this faster than the speed of light travel that would connect a lot of different parts of physics together. And that's why I kind of like it.
You know, there's certainly no lack of imagination in this field. It's a lot of fun, and I think that people get that impression from checking out your book. So you've been very indulgent. I have one last question to send folks home with. What about the theory that God did it? Why can't I just say that? And I'm not just, trying to stir trouble. You talk about this very explicitly in the book, which I kind of like. So, Phil, where's the evidence for this? What is the prediction for the cosmic microwave background if God made the universe?
Well, we do see Stephen Hawking's signature in the cosmic microwave background. His initials are there. And when you have someone who's painted a painting, they usually put their signatures in it. So maybe Stephen
There you
Hawking
go.
made the universe. No, there is this thing called the Kalam cosmological argument. And it tries to argue from the Big Bang to God. And the idea, it goes something like this. Everything that begins to exist has a cause. The universe began to exist. The universe must have a cause. And then you do some analysis and you say, well, the cause must be a personal agent with free will, and so on and so forth. And we've been critical of this argument. And Sean, you starred in one of our films critical of this argument. So people can go on the YouTube channel as well to Phil Halper to look for this. And the problem with this argument, one, it uses this old idea that the Big Bang was necessarily the beginning. And we don't know if that's true or not. It might be true. We're not claiming that the Big Bang wasn't the beginning. We're only claiming that we don't know whether it was. So we can't establish that premise. But then there's this issue of causality. Causality is a property of our lives. You know, when we take a vaccine and we go, oh, look, you know, hospitalizations of COVID dropped dramatically when the COVID vaccine came out. What caused that? Well, the COVID vaccine caused that. So yes, causality is part of our everyday lives, but it doesn't follow that it's there at the fundamental layer of existence. It may be an emergent property. And I know you've argued very much that causality is an old-fashioned way of talking about fundamental physics, that really we should just be thinking about equations and just forget about that's the eliminativist view popularized by Bertrand Russell. But I think the bottom line is we don't know whether causality is really there at the fundamental layer of reality. So I don't think there's any reason to think that the universe did have a cause if it did have a beginning, and we don't know whether it had a beginning. So I think this argument doesn't really work. Of course, there could be an intelligent being that created the universe. And in fact, one of the things we do mention briefly in the book is the idea that maybe you could make a universe in a lab. But if you could, it doesn't mean that the people that created it would be any kind of divine being. And in fact, there was one thing that we mentioned that got cut from the book. So I'm going to quickly mention it. And that this was proposed by Guth, Bari and Guven. And Alan Guth won an award for having the messiest office in Boston. So if you did come up with a way to create a universe, doesn't follow that you're a divine being.
Oh, I'm sad that got cut.
Yeah, me too.
Niayesh, any closing thoughts on this one?
So it's kind of interesting that there is this idea of God of gaps that, I mean, historically, wherever there were gaps in our understanding, we associated with God. So we had also stuff about eclipses and the storms and everything that we didn't understand in nature, we associated with God back in the days. And now that we understand the things better, we don't do that. Of course, you could still do that in a subtle way, that everything is created by God. But it's kind of this idea that maybe the beginning of the universe was creation by God. That's kind of that old-fashioned idea of we pushing the God of gaps to where our science stops. And right now, our science stops at the Big Bang. So we can put God there, and it's kind of the natural continuation of the God of gaps. Now, does that mean that's a theory? I mean, if we go by history, that means that historically we just managed to push that, and it gets harder now. But my suspicion is that we'll be able to push that God away. But then the question is that, I mean, does that mean that God is irrelevant for our personal lives? And I think that's a completely different question from whether God plays a role in scientific endeavor. And I think we should really separate these two from each other.
That's perfectly fair. I mean, at least I don't know which there are more of, major world religions or theories of what happened before the Big Bang. So there's a certain parallelism, and the different sects cannot quite come together and agree. So I hope that people check out your new text talking about these things. Phil Halper and Niayesh Afshordi, thanks so much for being on the Mindscape podcast.
Thank you. It's been a pleasure.
Thank you, Sean.